asteroid physics side, is that correct?
I didn't know about asteroids in my master's, but American supernovae in my PhD.
Right, okay.
But I did touch on the asteroids.
Okay, so thanks very much for coming along and talking to us this evening. Welcome.
Thank you very much. So this turned up, so let's hope it starts again. Yes.
Yes.
Huzzah. Okay, so thanks very much for the introduction and thank you so much for inviting me here today. I will be talking to you about what I call stellar depths and cosmic fireworks. Let me check there's no typo on the slide. No, it's fine. Good. And that's the usual title of all of the talks that I give at that kind of event, because it's vague enough that I can basically talk about everything I love. I can tell you about supernovae, I can tell you about kilonovae, and that's what I'm going to do today. So Carl Sagan has said, is that okay? Can everybody hear me? Okay.
Yep.
Yes. Carl Sagan said, well, made of star stuff. He would be 85 today, according to Twitter, I believe him. And he was right, you know, the calcium in your bones, the oxygen in your lungs, the iron in your blood, all came from supernovae, the depths of massive stars. And in fact, everything that you're made of, all of the elements in the universe, apart from hydrogen and helium, came from stars. There's a few other ones, you know, that come from very weird stuff that can happen in deep space, but everything else came from a star. So if we look at oxygen, iron, and calcium, the stuff that's in you that I just mentioned, that originated in exploding massive stars and exploding white dwarfs. That's just two different types of supernovae that we're going to cover in the first part of this talk. But that's not it. All the aluminium, the silicon, the copper that's in your technology, in your phone, in your telly, all of that, that also came from supernovae. So say thank you to the heavens for your Twitter. And also the shinier stuff that we love to spend a lot of money on, like gold, platinum, silver, palladium. That's the stuff in your jewellery, and that came from a different type of event, emerging neutron star, which we now call kilonovae. And dynamo stars, but they're more boring, so I'll skip that today. And that will be the second part of our talk. So the supernovae is more related to what I did in my PhD. The kilonovae is what I'm studying at the moment. It ties in pretty nicely with my research, and I'm happy to talk about that after the talk, but we're going to stay nice and friendly for the next like 30 or 40 minutes. So, star, this is my artist impression of a star because I couldn't be bothered to draw a circle. So before we talk about these really impressive stellar explosions, we need to go back to basics and ask ourselves the simple question, what's a star? And to make my life easier, I will ask you the question, what is a star? I'm actually expecting some details to that, otherwise we're not moving on.
Ball of gas.
Yeah, guess.
Slowly cooling to a solid mass.
Huh?
Slowly cooling to a solid mass.
Ooh, that's very interesting. That is true of some of them. So the white dwarfs, which we're completely going on a tangent, but screw it, never mind, this is brilliant. White dwarfs are indeed just cooling very slowly, and eventually, unless something happens, which we'll see in a minute, they will crystallize and go to a temperature of exactly 0 degrees. And crazy things happen when you get to that kind of temperature, but you know, it's not the topic today. White dwarfs do that, but they are a stellar remnant, as we'll see in a minute. I'm talking about a star like our sun, something that is currently going through its normal life cycle. Does anybody have, yes, go on, Bill.
It's a ball of hydrogen and helium that's massive enough to initiate a proton-proton reaction.
Yes, that's what I wanted to hear. Fusion. Amazing. Yes, we need fusion. For a star to be going through its normal life cycle, we need fusion in the center. And the reason we need that is because the star is really big, you know, like the sun is about 1 million times heavier than the Earth. There's a lot of gravity going on that's pushing everything in, and if we don't do anything to counteract that gravity, then it's just going to collapse, which is not great if you want a nice, stable star that stays there for 10 billion years. So you need fusion to push everything out. Now, this ingredient, the balance between gravity and fusion, is something that we'll get back to several times during this talk, so keep that in mind. Now we're going to do something else with our stars. We're going to split them between low mass stars, which are less than 8 times the mass of the Sun when they are born, and the high mass stars, which are more than 8 times the mass of the Sun when they are born. The reason I'm emphasizing this when they are born business is because this is literally very important, right? Because these stars, especially the high mass ones, they will lose matter as they age, right? But what determines how they die and how they live their lives is their mass when they're born. So let's talk about the low mass ones first. This is a quick chain of the kind of fuels that we're going to need for our star to be living its life. So like Bill said, we're starting with hydrogen. Proton-proton chain that will turn hydrogen in the core of the star into helium. Now that's great, and that can go on for billions of years, but eventually you're going to run out of hydrogen. And the problem when you run out of fuel is that you've got nothing balancing the gravity that's pushing everything in. So you need to find a new fuel. But conveniently, you've made a crap ton of helium, so why not use that instead? And it works really well, and you take 3 helium, and you bang them together, you make a lot of energy, and then you get carbon. And that's great for a little while until you run out of helium as well. And then you're in a bit of trouble, see, because our low mass stars are not hot enough to burn carbon. Their core will never get hot enough. Let me explain that a little bit more, right? So we've got our gravity that's pushing everything. Fusion has stopped. The core is made completely of carbon, we've run out of helium, our fuel is gone, right? So gravity is pushing everything in, the core is contracting. As that is happening, energy is being released by the gravitational potential energy. Fancy word, essentially it gets really hot. It gets closer together, it gets really hot. But it never gets hot enough for carbon to ignite. And that's how our star will die, right? Because that heat just goes to the outer layers of the star and just makes them expand into space, and you get something really pretty, like the Helix Nebula. They're called planetary nebulae, nothing to do with planets, someone just got it a bit wrong a while ago, and they thought that looked like a planet, and they called it a planetary nebula, and never bothered to change the name. That's a recurring theme in astronomy, someone getting something very wrong and people sticking with it. History, hooray! So these are called planetary nebulae. So these fancy filaments here are the outer envelope of the star. But inside of that nebula, we'll find a white dwarf, the stellar remnant that we were talking about earlier, right? So the core of that low mass star, that ball of carbon that got hot but could never ignite the carbon, right? That is our white dwarf. That's about the size of the Earth, but half the size of the Sun on average. A bit more than that even. So it's very dense, right? Because since you run out of fuel, you don't have fusion, gravity pushed everything together as close as it could physically get, essentially. Now, things get really interesting if our white dwarf has a little friend. And that actually happens relatively frequently. Stars like to go together. But if you have a companion, and that companion gets a little too close, you can have mass transfer between the 2 objects, and our white dwarf can start gaining mass. Now, white dwarfs are a bit special because their matter is pushed together as close as it can get. They have a critical mass, a critical limit. And when they reach that critical limit, fusion starts. Essentially, it got massive enough so that it got hot enough so that the carbon ignited. That's ace. The problem is that matter isn't quite in the state that it was when it was inside our star. The situation is a bit different. It's a type of matter we call degenerate. It's like another phase of matter. You know, you've got ice, you've got solids, you've got liquids, you've got gas, you've got plasma, and you've got degenerate matter. Essentially, things are so close together that there's no room for anything else. And that does something funky, where if you increase the temperature of degenerate matter, Now that has a very interesting consequence. So if your fusion starts, it will release a lot of energy. But if that energy then goes in to increase the temperature, and that temperature does not make your star expand, that temperature, that energy, has nowhere to go. So all it's going to do is increase the rate of fusion, which is going to increase the energy and the temperature, etc., etc. And you can see it's a circle. It's what we call a thermonuclear runaway. Essentially, your star goes boom, and you get really pretty things like this. These are thermonuclear supernovae. They're nice and pretty. They're round. The other ones that we'll see in a minute are less round. They're my favourite, but these ones are okay, I guess. And actually, these two were observed. This is Tycho's, and this is Kepler's. All the other way around, I always forget. Thank you. And yes, that's what happens 300 years after your star has exploded. A beautiful supernova remnant, and nothing in the middle, because your white dwarf was completely disrupted by that thermonuclear runaway, by that explosion. Now, that's enough of the low mass stars. Let's move on to the high mass stars, which are my personal favorite. So we're back to our chain of fuels. We start with hydrogen, like Bill said, proton-proton chain. We make some helium, and then when we're out of that, we make some carbon. But in this case, the star is big enough, the core is big enough, that when everything condenses, right, when that gravity takes over and gravitational potential energy is being released, there's so much mass, that so much energy is released that it will get hot enough to ignite that carbon. And in fact, this keeps happening until you reach iron. Now there's a little problem when you reach iron, is that you can't really use it as fuel. It's just a bit useless. And the reason for that is that if you try to bang two nuclei of iron together, they don't make any energy. So we've got a graph that's a bit ugly, so I'll try to walk you through it. This is what we call the average binding energy per nucleon. Long story short is how much energy you get when you bang two of those together. The bigger the gap, the bigger the energy. So between hydrogen, which is what we use as fuel originally, and helium, which is what we make, right? The product, between the fuel and the product, there's a massive gap, you make a lot of energy. But see that gap, like for example between helium and carbon, that's a lot smaller, between carbon and oxygen, that's a lot smaller. That gap keeps getting shorter and shorter and shorter. That means you make less and less energy. And when you get to iron, well, that goes down, right?
Yeah.
Well, that means that you don't make energy, you take energy from the system. And it's a kind of a crap fuel if it takes energy away, right? It's not really doing anything. So all of these nuclei give you energy if you fuse them together, and all of these give you energy if you split them. So for example, look at that. That's plutonium, that's uranium, that's the kind of stuff you use in your nuclear plants, nuclear fission. That's what gives you energy in that case. So when your star gets to a point when its core is entirely made of iron, what does it do? It collapses, because there's nothing else to do. Gravity wins. That's it. In a quarter of a second, the equivalent of the mass of the sun is condensed into an object about 20 kilometers across, about the size of a city. And the pressure is such, this object is so dense, that the protons and the electrons are forced together to make neutrons, and you get a neutron star. Now, that's not the end of the story, because there's the whole rest of the envelope of the star that's also falling in, less quickly but still going. And eventually it's going to meet that really dense neutron star, and it's going to bounce off of it. And you're going to get a massive wave of energy, a shockwave going through the star that starts to unbind it. Now, that's not actually quite enough to get the supernova, but we're getting technical, neutrinos are involved. But eventually you get, that's the core collapse, you get this! That's much prettier. Yes! CASSIOPEIA and the Prime Nebula are two of my favorite core collapse supernovae. And as you can see, they're a lot messier than the other ones. And that's not accidental. I mean, that's just the way that the explosion mechanism is. It's a lot messier when you've got massive stars involved. The white dwarf is tiny. It's really dense, really homogeneous. The massive star has this whole big fluffy envelope to explode into space, and there's a lot going on. I don't think either of these were observed visually. This is from 1054. The crab was seen.
The period was 1054.
1054 was
Chinese.
The Chinese still there. Cassiopeia wasn't observed, I don't think. But so yeah, this one is about 1,000 years old. This one is about 350 years old. And they're some of the most famous supernova remnants we've got out there. In fact, in CASSIOPEIA, see that little blue blob? That's the neutron star. You can actually see the neutron star. And in this picture, I'm actually an idiot, because there is a picture with the crab pulsar that is much better than this one. I don't know why I picked this one. It's amazing. You can see the swirls around the pulsar. It's beautiful. So yeah, so there it is. We've got two types of supernovae. Our thermonuclear supernovae, they leave no remnant. The white dwarf is completely unbound, and they mostly make iron. That's just because of the way that the explosion is. It just completely burns everything, and you make iron-type elements like nickel, cobalt, iron, obviously. And collapse supernovae, which come from our massive stars, they leave behind usually a neutron star, sometimes a pulsar. A pulsar is a fancy neutron star that has a lot of magnetic field and is spinning quickly, and so it sends jets, and you can use it to make clocks and stuff. Clocks and stuff. They're better than clocks, they actually are. And we've got intermediate mass elements coming out of these collapse supernovae, so like oxygen, calcium, that kind of stuff. We also have iron-type elements, but like 10 times less. So yeah, they're really cool in so many ways, not just because of what they make or because they explode, but just the sheer amount of energy that they release. Right? So this is 1994D. Oh, yeah, by the way, the name of the supernova is a bit silly. I mean, it's not silly, it's just phone numbers, right? It's the year and then letters. So this was in the 1990s, so we didn't find that many supernovae, so a single letter did all right. Now we find like 13,000 a year. So there's like 6 letters after this. It's getting impossible to figure out which one is which. So yeah, so they're really cool. This is not an artist impression, this is a real picture. And I want to emphasize this because they can outshine their own galaxy. I'm not lying, this is true. See this supernova as bright as the center of the galaxy? They're incredible. They release as much energy as the sun will in its entire 10 billion year lifetime. Only like 10% of this energy goes into accelerating the ejector, at least for the core collapse, and they can go at speeds of 10,000 kilometers per second. I'm not exaggerating, this is not an upper limit, this is an average, right? Like, I've worked on supernovae that had ejector speeds of 30,000 kilometers per second, so I'm not inflating all of these numbers. This is pretty middle of the road supernova. And so, because they release so much light and so much energy, most of these supernovae that we see are from other galaxies. Right? The 30,000 that I mentioned that we saw in 2019, all of them from other galaxies. Because in fact, they're really rare. Because you need these really massive stars to make supernovae, and massive stars are the rarer stars in the universe. Like in the Milky Way, we can expect about 2 supernovae per century. And that's an average, like we haven't seen one in a long time. The closest one we've seen recently was from the Large Magellanic Cloud, which is like a satellite galaxy of the Milky Way. That was in the late 80s, and nothing since. I mean, some galaxies have much more active environments, like the Firework galaxies right here. In the past 100 years, we've seen 10 supernovae in this galaxy, which is very fruitful, and we actually expect more to come. One of my ex-supervisors actually imaged loads of the stars, the massive stars in this galaxy, to try and get a good picture of them, because if they go through in the next few years, we'll have a before and after, which is pretty awesome. Anyway, supernovae are awesome, but what's next, right? So it's the death of a star, but in the case of core collapse, there is something left behind, so maybe we can do something with it. So if our core collapse supernova was in a binary system, and if we're lucky enough, oh sorry, apologies for that word, there's jargon, that is a Gen Z jargon. That just means if the two supernovae didn't fling the companion out of the orbit of our primary star. I gave that talk to students earlier this year, so I tried to appeal to them with young people speak. I am not one of them, unfortunately. So if we've got a binary system, and that binary system undergoes our two supernovae without being disrupted, right? Because if we want two neutron stars, we need two core collapse supernovae. And if these two stars are close enough that they will merge within the lifetime of the universe, which is not that simple, then we can get a neutron star merger. This is an artist impression. I thought I mentioned it. Like you haven't seen it this close. This is from NASA. I should have written it in there display there. Yeah, we can get a neutron star merger, which is brilliant. So, but not that simple. Because although binary systems are very common, especially for massive stars, right? Most massive stars, if not 100%, are in binary systems or in triple systems. These two conditions are more difficult to work out, right? Because if our two stars are close enough to each other that they will interact and then merge at some point at the end of their lives, then they might be close enough that the core collapse supernovae, which, like I said, are very energetic explosions, they might disrupt it, you know? But let's say that these conditions are all put together, and we've got the reason that our neutron stars will merge eventually, if the core collapse didn't disrupt their orbit, is because of gravitational waves, which is something that everyone's hopping on that train in my field at the moment. Like everyone does gravitational waves. We saw the first ones in 2015. We saw the first neutron star merger gravitational wave stuff in 2017, and since then everyone's on it. And the reason they're so cool is because they can take away energy from the orbit of your star. So let me demonstrate. Not demonstrate. I will mime it. Ooh, ow, ow. So, yes. Okay, we've got neutron stars, and they are disrupting. They are what's the word? Reforming? That's the French word. Sorry. I'm having a bilingual moment. Never mind. So you know, you know how the fabric of space-time can be. What's the bloody word? Help me. Just participate. Come on, we've got a big room. We'll figure it out. Huh? Déformé. Non?
Déformé.
Déformé. Bent.
Distortion.
Warped. Thank you. Yes. Warped. Anyway, so big masses like neutron stars can warp the fabric of space-time. Fantastic. Teamwork. Any mass can warp the fabric of space-time. The sun can do it as well. In fact, it's doing it right now because we're going in orbit around it. Right? It's doing it very well. But something like a neutron star, because it's so dense, does it to a much greater extent. It's extreme, right? And if they're very close together, and they're both warping the fabric of space-time, and they go around each other, they're going to send ripples in the fabric of space-time. These are the gravitational waves we're talking about. Now, these gravitational waves carry energy away. And they need to take it from somewhere, and they're obviously going to take it from the orbit, since this is what's causing them. And if you take energy away from the orbit, then your stars are going to start coming together. But the closer they are together, the higher the frequency, the amplitude of these gravitational waves, and so they're going to take away more energy, and so this is kind of a self-feeding sort of system. And so eventually, your neutron stars are bound to merge, right? Now, I'm going to attempt to explain very briefly how the interferometers that are used at LIGO and Virgo, the gravitational wave detectors, work. This is a first-order approximation. Please do not ask me any further questions because I do not understand how to explain. This is very complicated physics, but I can give you the first order approximation that we can all understand. I've got a little animation that I did not make. Yeah, it's brilliant. We've got a big laser, and it's shooting at two mirrors, right, splitting the beam. Now, these mirrors are free to move in space. They're completely isolated from their environment. Now, that laser, the signal is completely in sync, and then it is split between those two orthogonal directions, so 90-degree directions. And yes, this is reflected by both mirrors individually and then put back together here onto our detector. And if the distance is where it's supposed to be, then the peaks and the troughs align, and you've got what we call destructive interference. Anyway, so if our mirrors move and the relative distance changes, that's also going to change the relative position of these peaks and these troughs. If peaks align, we've got constructive interference, we've got signal. If peaks and troughs align, we cancel each other out, and we don't get a signal. That is the basics of the interferometry. And the reason it's called interferometry is because one peak might interfere with the trough and cancel out the signal. That's essentially the idea. Now, there's a lot more going on at LIGO when we get signals, right? And so, oh, by the way, the reason these mirrors move, if that wasn't necessarily clear, is because of the gravitational wave, because it moves space-time. The space between the mirrors will change as the gravitational wave passes through our location on Earth, and because there are right angles, the distance between the mirrors will change differently depending on the orientation of that gravitational wave. Now, the reason this is a first-order approximation and that everything is very complicated anytime you talk about gravitational wave is because the distances involved are incredibly small. So the type of motion you expect, the distance difference you would expect between the mirrors as the gravitational wave passes through is of the order of 10 to the minus 90 meters. That's 0.18 zeros and a 1. It's tiny. To give you an idea, okay, like an atom is, the diameter of an atom is 10 to the minus 15 meters. It's 10,000 times bigger. I don't know how they do it. I legitimately don't. Like, there's a lot of machine learning involved, and the physics is very complicated. The lasers, oh my god, the lasers are very complicated. The mirrors are incredible. Like, this is one of the mirrors I was talking about. This thing is 40 kilos. The whole pendulum is 360 kilograms. And it's got to make sure that this is completely isolated from everything on Earth. Like any little earthquake, anything. I know someone at Sheffield who, in my previous institute, who worked in LIGO, and he was telling us that they spent like weeks looking for a signal or like a source of noise, and they could not understand what it was. It was birds pecking at a pipe like 2 kilometers away, like near one at the other end of one of these tubes, and they can detect that. It's unbelievable, the work that they do. Anyway, long story short, we can detect gravitational waves, right? So we've got a signal from the ripples, right, from the change of distance caused by the gravitational waves. The frequency, the amplitude increases until you get the merger, and then it dies down. So that's short for gravitational waves. And for neutron star mergers, that kind of signal that we can observe, that we can measure, is of the order of 100 seconds. So it's not long, but it's not too bad. Now, when we have a neutron star merger, this is not the only thing that we're going to get, fortunately. And that's why we call this new era of astronomy multi-messenger astronomy. It's because we use loads of different techniques to observe a single object. One of the other techniques that we can use is to look for short gamma ray bursts. Sorry, I'm out of room in this slide, so I'm using abbreviations. I will repeat it several times. So short gamma ray bursts are short, less than 2 seconds, as opposed to long gamma ray bursts, which are longer than 2 seconds. I know, right? Sometimes science makes sense. And they're from completely different objects, so I'm not going to mention them again today. Anyway, the short gamma ray bursts and neutron star mergers arise because you have, as your stars merge, a disk, an accretion disk might form briefly and collimate two jets that are very energetic, relativistic materials just plowing through space, and you get those gamma ray bursts. But you've got to be, you know, you've got to be aligned with those gamma ray bursts to see them. Like if you're here, you're not going to see it, unfortunately. But that's not it, because we can also get to see the kilonova. This is my very poor impression of a kilonova, and it goes in all directions, which is lucky because that means we can see it more than the short gamma ray burst. And this lasts for a few days, right? So not quite as long as a supernova, which would last a few weeks, maybe a few months if you're observing a big one. But this will go on for a few days. And this is from the ejector of the merger. Because the merger is messy, right? You don't just, it's not like putting two bits of Play-Doh together. There's going to be material flying around, not just from the disk and the jet, but it's just going to go everywhere and in all directions. And this ejector is what's going to allow you to make these really cool elements that we were talking about earlier. The gold, the platinum, the silver, there's also rare earth elements, lanthanide going on there. The reason I've got the word art process here is because I used this slide for a lecture a few weeks ago. But it's not too complicated. The idea of art process, R is for rapid process, and rapid because you're rapidly firing neutrons at your atoms, which is relatively easy to do when you're banging two neutron stars together. There's a lot of neutrons to go about. So that's why you make these elements. It's the only way to make them, right? This is the only process that can make platinum, gold, silver, and the gang, because they're very neutron rich. If you don't have the flux of neutrons, you're going to make elements that will decay before they get to that stable point. Right, so let's talk about some real kilonovae which we've seen, and by kilonovae the one, we've seen one. Well, I mean, one that has had the whole triad, right? We've got the gravitational waves, the GRB, the transient. That's 170817, and that's the first gravitational wave we detected for a neutron-star merger. And luckily enough, we got everything with it. We got the gamma ray burst less than 2 seconds later. It also lasted less than 2 seconds, so it's good. Because until then, we didn't have, a smoking gun telling us, oh yes, definitely short gamma ray bursts are from neutron star mergers. Like, people had a fair idea that was the case, but we didn't know for sure, but now we do. And we also found the coincident transients. So the transients are just all things that just don't last in the sky. Supernova transients, kilonova transients. And it was really, really nearby. So let me tell you why we were so lucky with 170817. And I'm going to show you a real piece of data. The reason this looks so noisy is because it is. That's just what you deal with in science. Again, I don't know how they do their magic. Like, this is clean. This is cleaned up. This is the final result of what they do in their papers. But this is the frequency of the gravitational waves, and as we said, they increase until we get to the merger, and then it stops, because once you only have one object, no more gravitational waves. So we've got the LIGO detectors, both in America, we've got Virgo in Italy, and as you can see, it just goes nicely up until the merger. We can see it in LIGO Hanford, we can see it in Livingston, and if you can see it in Virgo, then you need glasses because there's nothing in there. I mean, maybe you're seeing something, but it's not a gravitational wave. No, we didn't see anything in Virgo. It was on, but there was nothing detected. And that was very lucky. And the reason it was so lucky is because those interferometers, in both hands, have the mirrors, oh my god, put it at 90 degrees, right? So if this mirror is moving in this direction, we'll see the gravitational wave, right? If it's passing vertically. If it's passing in this direction, this mirror here will move like this, and you will see your signal. If the gravitational wave is passing in this direction, both of them will move like this, and so their relative distance doesn't change. That means that every single one of these detectors has a blind spot. And this was brilliant because it helped us triangulate the location of 170870. Because, to be honest, it's really tough to find the location of these gravitational waves. These are some of the sky maps, the early sky maps from the Niger-Berger collaboration. And these areas, which we call bananas, I'm not joking, because they look like bananas in the sky, there would be the search area that people would have to look through, see through, to try and find the short gamma ray burst and transient counterpart to that gravitational wave. Very, very difficult. But 170817 was tiny. Because we had that blind spot and because we had the short gamma ray burst, it was detected 1.74 seconds after the gravitational wave. So they put all of that data together to give us a very small search area. And we're very lucky now to have telescopes that have gone so much better at searching the sky. I can't remember which one found it. Never mind, doesn't matter. So we've got dedicated surveys, and this is just a comparison of how it's evolved over the past decade. So PTF, IPTF was one of the first ones, which I think finished in 2012. ZTF is a new version that started last year, before. This is the moon by comparison, right? This is Andromeda by comparison. So these search areas are massive compared to usual telescopes that we'd use to look at one single object. Oh my gosh, yes. Sorry, I'm just remembering the things that I added today. This, for example, because I just showed you sky maps, I wanted to show you this. This happened today, and this is one of those moments where scientists are like, I don't know. So normally we expect bananas or like kind of big search areas, but this, what is going on here? Like tiger stripes. This is not a fluke. This is not terrestrial. This is not noise. They have checked somewhat thoroughly. They confirmed this is a real alert from space. But they don't have models for it, so they don't know how far it is, they don't know what it is. Some people in my collaboration were suggesting maybe it's a galactic event, maybe a supernova or a neutron star did something funky and sent out some gravitational waves. We have no idea. This is one of those, we don't know, moments. So, this was funny to me, maybe it's not. Yeah, fucked up sky maps. Anyway, we found it. 170817 is 2017 GFO, which I can't help but read the book out. This is just me, maybe. And there's a little animated GIF showing you how it's decaying over just a few days, right? So August 22nd was when it was found. Well, no, it is after it was found. Anyway, 26th and 28th. Very quickly, it decays. This is the light curve that we've got for it. You can see that it peaks very early in different colors. So by the way, this, maybe this is a nonsense to y'all, but this is a redder essentially as you go. The redder you go, the later is the peak. That's pretty standard with that kind of ejector. It happens in supernovae as well, and that shape is pretty standard again for that kind of ejector. For supernovae, you have that kind of shape as well, except they last 5 times longer. Like the peak happens around here, and they just decay over more time. And that's just because this is a radioactive decay sort of profile, and it's just different radioactive elements, because you just have more neutrons, there's fancier stuff happening here than in supernovae, so they just behave slightly differently. Now, we're getting to the end of my talk because I'm tired of hearing myself speak. But let me summarize very briefly. So we've got supernovae, which I told you about today. By the way, I can say supernovae because it's plural. We don't say supernovas. It's a supernovae, AE. Yeah, that's just the pedantic in me. And we've looked at two different types of supernovae, the ones from the low mass stars, the ones from the high mass stars, how they create the elements that we need to survive, the oxygen, the calcium, the iron. We looked at the kilonovae that make some of the fancier things that we like to wear, some of the rare elements in the universe that are a lot harder to make because you just need a lot of energy and a lot of neutrons in the same place in the same time. And this is really a growing field. The supernova field has been going strong for about 2 decades now. It's time for kilonovae to take over. But one thing I have not really addressed is why are they called supernova and kilonova? That's fancy, like why would we do that? And it's to do with our white dwarfs again. And I'll finish on this because I just find it really funny how we do things in astronomy. That is one of the great mysteries of the universe. So we've got a white dwarf and it's absorbing mass, right? And I gave you this slide to tell you about the thermonuclear supernova. But I don't even think this is why Mark Garlick made this picture, because I know the people who hired that dude to make these pictures. I think this is for a cataclysmic variable, which basically starts the same. You have a companion to white dwarf, it gives it a lot of mass. But what happens is that the explosion occurs before it reaches that critical mass I was talking about. So you don't disrupt the white dwarf entirely, it stays there, and then it will accrete more mass, and it will go boom again. This explosion is called a nova. And these have been known for a long time. They've been observed for hundreds of years, but in the early 20th century, people found novae that were much brighter. And because astronomers are so creative, they call them supernovae. And then they realized they weren't novae at all, but they were like, oh well, never mind. Because now we're using the word and we can't make people change the way that they speak, so we'll stick to it. And that's why we have the word supernovae. And following along that same train of thought, when people were originally making models for neutron star mergers and the energy in neutron star mergers, they found something of the order of 1,000 times that of a nova, and so they called it kilonova, because kilo is 1,000. I don't think these models are right anymore. I don't know, but I can assure you that even if they're wrong, we're going to keep using that word because now we're stuck with it. So yeah, naming in astronomy is, you better get it right, otherwise it's going to be wrong forever. Anyway, thank you very much.
Thanks very much, Eloise. That was really informative and enthusiastic talk. I'm sure there'll be lots of questions from the audience.
Yes?
Yes, what dictates when a white dwarf and its companion, when you get them a transfer of material, what dictates whether it happens to create a nova or your type 1a supernova?
That's a very good question. My partner actually works on that stuff. So the nova will happen if you get so much material outside of that white dwarf, because it actually doesn't really merge with it, kind of sits outside, because it's mostly hydrogen that is transferred onto the carbon, right? And it's not as dense, so it just sits at the top. But it gets quite dense, and eventually you get both a thermonuclear runaway and an explosion, and that's how you get the nova. We don't really know. And this is actually, okay, two things. First, this is not the only way to make a thermonuclear supernova. You can just take two white dwarfs and bang them together. This is a very effective way to do it. That is also, that one of the companions is also possible, but the question is, how do you get through that nova stage thing without losing too much mass? The question is, do you lose mass when you have the nova, or have you accumulated sufficient mass that you get an explosion, but your white dwarf has still increased in mass, so that you will eventually tend towards the supernova stage? That is still an open question, and people debate whether it is the so-called single degenerate with one degenerate white dwarf and a non-degenerate companion, or double degenerate with two white dwarfs scenario. There are some crazy people saying that there are other ways to do it.
fairly well-known recurrent nova in the southern hemisphere, T. Pixidus, which had a flare up, it was about 7 or 8 years ago. And,
There are record of novena, but
so there's some speculation as to whether that's close to the Chandrasekhar limit, that particular
like I said, we
white
know certain novae that happen every year.
Mm.
We've got, it's incredible. Some record novae are, and their recurrence rate is like, it's getting shorter between the outbursts, at least, not as in novae, but like it's a very interesting topic. So yeah, right.
Well, Yuri?
Regarding our sun, the 11-year solar cycle, I was reading something I forgot. Was it to do with like a gravitational, say, threshold change in the sun at a certain latitude for the start of the solar cycle? And I'm wondering if it's kept in, say, first year, or for example, that tiger pattern picking up, could that be related, say, to like the near field of the sun getting into?
Oh, the funky pattern? No, it's not going to be something to do with the sun. No, because that kind of, I mean, anything that's very close to us would be a much. It depends on the amplitude of the gravitational wave. This is of the kilohertz order, which is why some people are thinking this is galactic, and some people have a few avenues to explore. But yes, we'll see what they say in the near future.
What do you mean by the word Newton? J-E-E-T-I-N-G. What do you mean on the slides on that word?
Sorry?
What do you mean with the word on the slide? You mean the jargon and
Yeeting.
what?
Yeeting. That's the jargon word. It's yeet. You yeet something. It's just, it's not scientific jargon. It's yeah. Yeet me your thing. Yeah, I don't know.
No, that was not the intent.
Okay.
When you say that, am I correct when you said that two neutron stars, they can collide?
Yeah.
And if they collide, they form elements.
Yes.
How do stars that have condensed matter, were just neutrons, nothing, no protons, no electrons, nothing inside, how do you make an atom out of that?
Just neutrons. That's the thing. It's never just. There's never just one thing. I have a graphic somewhere that it's just. They're not made of just neutrons. There's actually an iron crust even around the neutron star. It's heavily stratified, right? So at the core, you'll probably have mostly neutrons, maybe even strange matter. Ooh, you don't know what's in there, you can't see. But like the top layer is a thin crust of a lattice even of iron atoms, and underneath you'll have a kind of soup with remnants of iron that's kind of melting into this weird, because it's just a weird phase of matter. It's so dense. Like this. Oh my God! Yeah, just remember that. Sorry. Like deeper in the star, the neutrons are so weird, and the nuclei are kind of dissolving. The heavy nuclei that you get at the end of the supernova, they're dissolving. That you get this phase of matter called nucleopasta. I kid you not, this is the official term, because you get these weird like strands which are like spaghetti, these weird sheets that are like lasagna, and these weird balls that are like meatballs. It's like, oh my gosh, naming in astronomy, it's fantastic. The jokes write themselves. But yeah, so it's not just neutrons. You're right, if you just had neutrons, like it wouldn't come out of anywhere. That's absolutely correct. It's just trace elements of other things, and that's where it stems from. Yeah.
John, did you have a question?
Are neutron stars actually blue?
That's a very good question. I guess we would see them as blue. So the neutron stars are so hot that they will peak very far in, like, maybe even early X-ray. But because of the way the black body spectrum works, even if you peak blue up, I need the graph. You still make more energy in red wavelengths than the redder object. So it would look very, very blue to us. I can draw you the graphic later, it's just very hard to explain. But yes, it would look blue to us, but if we could see an X-ray, it would look X-ray. You know what I mean?
actually, I just remembered from that other question about the surface of a neutron star. There's a science fiction story. It's pretty fanciful by, I think, Robert Ford. I think it's called Dragon's Egg, where he has this scenario where there's actually creatures living on the surface of a neutron star and made of degenerate matter and are powered by nuclear reactions. They have sort of the same mass as a human, but they're only the size of a sesame seed or something like that. And
I mean,
they're real on the surface.
They would have to be, because the surface of neutron star is so smooth because of the density that there can't be any bumps higher than 5 millimeters or something. It's as if on the surface of Paris, it was so smooth there wasn't a pebble higher than an inch, which is insane. But yeah, sesame seeds, totally weird.
It's kind of a crazy idea, but anyway.
The type 1A supernovae, I mean, that they must be the neutrons, but the white dwarf must be described on the Chandler-Seeger limit. Isn't it that's the trigger point, they're a hair trigger?
Yeah.
And they use some distance determination.
Oh yeah, they are used as distance determination because, but there's like political debates now, like are they sub-Chandler-Seeger, are they super Chandler-Seeger, you know, can that mess with your distance determination? We think that probably it's more like sub-Chandler-Seeger when they explode, because what really triggers them is actually that there's so much matter that's accumulated just outside of the white dwarf that you get what we call a double detonation. So you've had loads of hydrogen and helium piling on around that white dwarf, and it's actually started fusing. You know, it's done its job. It got really hot, started fusing, made loads of helium, and that helium turns degenerate as well. And eventually that helium ignites, and you get that same thermonuclear runaway, and that then triggers the carbon ignition as a thermonuclear runaway, and so you get that double detonation. It's a pretty popular scenario at the moment. It might not be the only way to get a type 1A supernova. There might be, like, these scenarios are not mutually exclusive. You might get all of them just at different points in the life of different stars. But in that case, they don't have to be quite at the Chandler-Seeger limit to actually explode.
What about mergers of white dwarfs? Is that a possibility?
Definitely, yeah. That is definitely a possibility.
Okay, if there's no more questions, we've got supper out here tonight because Scardo have got a function, set up for a function in the Matariki room, and I'm sure you can talk to Eloise afterwards as well, but I'd like to thank Eloise again for coming and afterwards, anybody can stay around to help tidy up.